So here's a graph, and you'll notice that all log normal distributions are 0 at 0, even though you can't plug the value 0 into the density function because the log of 0 is minus infinity. It should be clear to you that as y goes to 0, the log of y goes to minus infinity. Then we're squaring it in that exponential, and it's going to drive the value of the density function to 0. So it shouldn't surprise you that the density function start at 0, which is the limit as x goes to minus infinity. And then the significance of the variance of 1 or 1.5 has to do with the dispersion of the log normal distribution. All log normal distributions have this asymmetry related to the fact that they're defined from 0 to infinity. And so consequently, they can't be symmetric. And so they always have this skewness. They have a fat right tail relative to the left side. But the dispersion goes with the parameter v squared, that as the variance of the normal parameter increases, the dispersion of the log normal distribution also increases. So now I want to talk a little bit about the mean and the variance of the log normal. I made the point that while m and v squared are the parameters that we use to define y, they are not the mean and the variance of y. They're the mean and the variance of the defining normal variable. So here we're going to calculate the mean and the variance. And the actual mean of the log normal distribution is e to the m plus a half v squared. Now, how do you derive that? Well, it comes from the normal distribution, where we made the point earlier that instead of using y and the log normal density function, I can use e to the x and the normal density function. We just saw that derivation. And in fact, using the normal density function, what is the expected value of e to the x? Well, that's just the moment generating function of the normal evaluated at 1. And we saw that formula earlier. If we take the moment generating function of a normal evaluated at 1, we get the expression e to the mean plus a half variance. And in fact, this generalizes that the general moment of y is the moment generating function of x evaluated at n. The nth moment for any n. This calculation, if I want to square y, the expectation of x squared, the expectation of y squared is the expectation of e to the 2x. Well, that's the moment generating function evaluated at 2. So I can actually write down the general formula for the nth moment of the normal. It's e to the n mu plus a half, it's not mu. Let me just do it this way. It's e to the n m, because we're using m as the mean of the normal, not mu, plus a half the variance, v squared, times, instead of t squared, we have n squared. So if I let n be 1, I get the first moment. I let n be 2, I get the second moment, and so forth. So every moment of the log normal, you can simply write down the expression because they're all related to the moment generating function of the normal. And from that, we can then get a formula. There's a note here relating to Jensen, namely that notice that the expected value of y, which is the same as the expected value of e to the x, is bigger than e to the expected value of x. Notice that in the exponent, it's not just e to the m, it's e to the m plus something. And that's Jensen's inequality because e to the x is convex. From that moment generating function, I can also write down the variance. Why? Because the variance is by definition the expectation of the second moment of y minus the mean squared. You all know that formula. If you go back to the formulas we just derived and you do the math, then you have this expression. So notice that by writing the variance of y using the mean of y expression, it's just a way of writing it. You can go from the parameters of the mean and the variance of the normal, you can go to the mean and the variance of the log normal, and conversely. I'll do an example now, but obviously if you are given m and v squared, you can easily write down the mean and the variance of y, the associated log normal. Why? Because both the mean and the variance of y are defined explicitly in terms of m and v squared. So if you're given m and v squared, you can easily write down the mean and the variance of the log normal. There's the expression for the mean, here's the expression for the variance. How about going backwards? What if you were given the mean and the variance of the log normal distribution, and you were asked, what's the mean and the variance of the normal distribution that gives rise to it? And these formulas can easily be used. I'll do a simple example. Imagine that you're given that the expected value of y is 2, and that we'll assume that the variance of y is 8. Well, we just saw in the prior slide that the variance, I'll shortcut this to v, the variance is equal to the mean squared times e to the v squared minus 1. In other words, the variance of the log normal is equal to the mean of the log normal squared times e to the v squared minus 1, v squared being the variance of the normal. So now this is easy to solve. We plug in 8 and 2, and we divide and we add, and we get e to the v squared is equal to 3. So we therefore easily conclude that the variance is just a log of 3. Okay? Standard deviation of square root of that. So once I get the v squared term, I can easily find the m. Why? Because I have an expression that the mean of y is equal to e to the m times e to the half v squared. So I know the mean of y, 2, is equal to e to the m, and e to the half v squared, of course, is the square root of e to the v squared. So I get square root of 3. So I finally get m is the natural log of 2 over square root of 3. So you can go from the moments of the normal to the moments of the log normal directly, and with just a little bit of algebra you can go from the moments of the log normal back to the moments of the normal.